Right? Think about the person that when you go into when you talk with a lot of friends, and that you have to talk with that person, right? Okay, the second that's the first phenomenon. Second phenomenon is actually the thing that comes together with preferential attachment, but not the same, and it's actually quote to be like uh, the name itself is actually has become quite a catchphrase in Hollywood movies, like talk about small world network, a small world phenomenon. Like when some people say this is a small world, you are referring to this small world phenomenon, I think. So the small world phenomenon express two properties of that. The first one is that the average length of the shortest path, if you calculate the shortest path from all of the connection together, the average length of the shortest path between pairs would be small. That's called small world, because if you say you connect to this person, disconnect to another person, and then you kind of express the whole network, calculating the average length, this number would be small. That is small world network, right? And actually, real world networks is like that, surprisingly. Okay, and another property is that the clustering coefficient is small. This is important. Or the local cluster coefficient is actually a small value. This is the value is a fraction of pair of node, the friend of the pairs. Sorry, the fraction of pairs of node friends that are friends with each other. Right. So in network X, I think it's measure the number of triangle or transitivity that node have, uh, dividing by the total number of transitivity that the network have. We can check that in the manual again. Right? So the clustering coefficient would be small. That means the network would be dense, would be sparsely connected, right? Not densely connected. Okay, two properties: small world, low clustering coefficient. Okay. So there's this well-known Milgram small world experiment. That is quite ambitious back then in 1960. That the like this is like a mail chain experiment. Now you can think of like, I think if you think about this, think about the ice bucket challenge. There are a lot of challenges like that. It's actually like Milgram small experiment that when you calculate the hop between the challenge and then connecting a well-known person to you, it's actually maybe you have a small hop between you and the well-known person. So Milgram small experiment, they tried this. They chose 296 starters, people, and asked to forward letter. Right? They need to forward this letter to the target. Right? The target was the stockbroker in Boston, and the instruction would be this: right? The stockbroker need to send letters to the target if they know the target by firsthand. Like you want to send your letter to say for this maybe the Warren Buffett, or maybe you want to send this to Prime Minister. But well, we have email, right? Send letter to the people, to the target, if you know him or her by the first name basis. If you know them well, you send letters to that person. If you do not know the target, you try to send letter to someone that likely to you know, that you are close friend with, and more likely to know the target. You send mails to that person, right? And some information about the target. Okay, and Milgram measure the connection length, the chain length, and they find that the median of the chain length was 6. That's the name 6 degree of separation. The old movie. I don't know if you know that. And actually, the phrase that have been used in a lot of books, a lot of things. This is one example of Milgram experiment that it start from this state, and then mail go through this until it reach this location, right? So it's kind of then you kind of reach that person within this number of hop. The 6 degree of separation, the movie. We talk about theory here. So you and random person in the world, 6 degree means that you need 6 hop to get to know that person. So just by 6 degree. Okay, let's take a look at Milgram experiments that have been tried out readily in different contexts. This is the email experiment by Dots, Muhammad, and Watts that is published in Science, right, in 2003. You want to understand more about this, let's read the paper, search in Science and this paper. So there are 18 targets to reach in 30 different countries, and the participants are 60,000, and they have to create, send mail to the target if they know them, or send through the a chains of people that they think they should know them, right? Just like ice bucket challenge. So in terms of total number, there are like 24,000 message chains happen, and 300 reach the target. 300 of the participants reach the target. And after measuring the average path length is actually equal to 4. That means the distance between you and the target, random person that the experimenter just thought about, is actually about 4 hops. Okay. And there are also experiments that is similar to this one as well, like those that has done with the Microsoft Instant Messenger in 2008. Right, the nodes contain 240 million active users, and the edge contain the user engaged in two-way communication over the 1 month. And by measuring the connection between user, they find that the estimated path length of the entire network equals 7. Right. So mean for so it's like the 6 degree of separation. Now we have number of 7. There's number of hops that connect you to any person in the internet. They measure the heat map connectivity, and they find that it's kind of having high connectivity would occur in the high latitude, just like COVID. I don't know why. This is communication heat map between that. And you can take a look at the paper here. Planetary scale view on large instant message network in 2008. Okay, this is real world. In other example, they measure the clustering coefficient. That is for Facebook in 2011. They found that they have high average clustering coefficient with degree of 0.5, decrease degree 0.5 for degree equal 2, and 0.2 when degree equal 50. And for instant message, clustering coefficient is 0.13. For IMDb actor network, average is 0.74. The higher the number means that they are well connected, right? So when we think about it, the clustering coefficient, it would decrease if the network becomes more random. If the network is not random, like there are some type like false connection, then it's likely to have high connectivity. So I would say that Facebook, because of a lot of connection occurring, not in random, because we kind of having the actual connection. That's why it have high degree. But in the actual connectivity, you find that it has actually lower degree, lower clustering coefficient, and also having humps. So when we think about this, does the two having the similar property, or do they are they independent or are they dependent? What does it mean? It means that does preferential attachment cause small world, or the other way around, or are they different phenomena that need to be modeled separately? So graph that created using preferential attachment would have small shortest path length. That is the reason that I answered the first question that you asked me about why it's called scale free. I think it's this reason. But there's no mechanism in preferential attachment that guarantee that there will be low clustering coefficient. So by this, it means that it should be different phenomenon. right? Because it doesn't guarantee that to have, you can have preferential attachment, but high connectivity, like when we force, like in Barabasi, when we force number of edge to be high, then you can see that the hub would contains a lot of connection, and there will be like a lot of triangle. That means clustering coefficient will be high, right? So that's the thing. Okay, so in the small world, right? How to create the small world model? Right? This small world model requires two properties. That is, you need to have high clustering coefficient. Let me check again. Should be low clustering coefficient. Yes, please. High C, sorry, high C. L low.
You said that there is no mechanism to for the preferential attachment to favor triangle formation, but in Babarasi model, if you use M equals 2 or more, I noticed that the network tends to create lots of cycles.
Right. But it's
I think because the number of new edges grow faster than the number of new nodes being added.
True,
so,
and also because once you add two, you are likely to create triangle, right? That's true, right? And actually, I'm wrong here. Small world network would have high C and low L, right? So this is actually is need to have high C and low L, right? High C obviously have to be high, and low L mean the low length has to be small. Okay, so in terms of the Barabasi network, Albert algorithm, true, that is in a sense you can create high connectivity, high cluster coefficient. Problem is you can see that it's quite a bit unnatural there, because you kind of force people to always have three connections, right? So it doesn't kind of express the stochastic behavior of the actual human being that have that. So I think that, yeah, right. And also that's just for one algorithm. There are a lot of algorithms. Let me go back. There are a lot of other algorithms. This is just the basic one. There are a lot of other algorithms that can generate the scale-free network. But basically, what you want to create is this preferential attachment properties. So it doesn't have to be just the Barabasi way. Which actually, I think this one is actually look more natural than this one. This one is when kind of to get like two connection, always get two connection. This is like fixed somehow, right? Okay, so suppose that we have a types of network that like Barabasi, and you want to impose the small world model. How to do that, right? So that's the way, a guideline, and that allow you to do that is actually by starting with n node. Each node connect to the k neighbor. You have k neighbor connect to each node. Then we have these parameters, this probability p, right? Now we will go through each edge UV, right? Each edge UV with probability p. We will select a node W at random, and then change from UV to UW. Can anyone tell me why it creates a small world phenomenon this way? By just selecting some node, and then with this probability, these parameters, and then we change it to rewiring it to the new one. Why is it creating a small world phenomenon?
My question is, are we rewiring all the existing edges, or just pick one edge and modify it?
When they put it this way, is we considering each edge. That means all edges. Each edge would have the probability, certain probability to change. So that means you need to randomize one number out. right? When using uniform distribution randomized random out, if it's less than that probability, then rewiring it to random node, right? Random node from existing node. But why is it creating the small world? Right. So once you increase the randomness, right, from p equals 0, having no random at all. So for this one, it would be like if you random the number and then that number is more than, is less than, right? Less than p, then you kind of randomly picking the node out. So if p equals 0, that means no randomness at all. Then you have just regular connection. But when you increase p, you kind of increase the connection, increase the chance to just say hyperjump from neighbor to authors that you may know. And that's actually kind of shorten the path between this neighborhood and this neighborhood. So this is the reason when you start with the kind of the ring and the community, and you have a way that to kind of hyper jump to jump from one community to another community, you get the small world network. If you kind of increase it to 1, you get the random network, just network that randomly connected, right? So if you increase p, right, increase p, the average of shorted path length would decrease. If you increase p, the average of the clustering coefficient also decrease out of that. Okay, so it becomes more and more random. Once it becomes more random, then you have less likely to get the triangle out.